Inviting me to be here, and it's a real delight. It's my first time in Pensacola, so it's a real pleasure to be here, and I've enjoyed my stay so far. So I'm going to talk about computational thinking and a little bit about thinking about computing. And I'm going to start right away. So I'm going to start with my grand vision, that computational thinking will be a fundamental skill used by everyone in the world by the middle of the 21st century. Just like reading, writing, and arithmetic. That's how fundamental I imagine computational thinking will be, or should be. And of course, it's an incestuous vision in that computing and computers will enable the spread of computational thinking. Now, this vision has grave implications with respect to the research in any discipline that we conduct, as well as educational implications, which I will talk about a little bit, especially with respect to K through 12. And so if you are interested in this talk that I'm giving today, I wrote a very short article. It's only 3 pages long that appeared in CACM a few years ago. And it really captures a lot of what I'm going to say today. So computing. Let's first talk about computing. Computing is what I like to call the automation of abstractions. This is quite abstract, and I will try to explain what I mean by this. But I like to think about computing in terms of these 2 A's, automation and abstractions. And it really is this feedback loop that one has when you're abstracting from some physical world phenomenon, creating a mathematical model of this physical world phenomenon, and then analyzing the abstraction, doing sorts of manipulations of this abstraction, and in fact automating the abstraction that then tells us more about the physical world phenomenon that we're actually modeling. When I talk about automation, and this is a whole other talk I could give, so I'm just going to give this as a side note. When I talk about automation, I'm very careful to include that the automaton can be a human, or it could be a machine. After all, humans compute. We may not be as fast as machines, but in fact, there are some ways that humans are much, much better computers than machines. In other words, there are still some tasks that humans can solve better than machines. Vision is one example. Speech, natural language processing. A lot of the challenges of artificial intelligence are put forth for us as scientists because machines still can't do them as well as humans. But that's, if you will, just the base case. I also like to talk about humans and machines together. In fact, networks of humans and machines together as an automaton. So think now that you can bring together the intelligence of a human with the intelligence of a machine, networks of them. That itself is collective intelligence. That could be an automaton in my world of automation. So that's quite a powerful notion, very unusual, and I'm going to save that thought because I'm going to come back to it at the end of my talk. As I said, that's just part of the picture with respect to computing or computer science. But that's really not what I'm going to talk about for the most of my talk. I'm really going to focus on the abstraction part of computing. Computational thinking is really all about the process of abstraction. And let me just explain what I mean by that. First of all, it is choosing the right abstraction. Not every abstraction is going to be appropriate for the problem that you're trying to solve. So first you choose an abstraction. And then, by definition, an abstraction is ignoring irrelevant detail and encapsulating in this abstract model the details of importance. that means I'm immediately talking about at least two levels of interest. The level I'm ignoring the detail from and the level of interest. So the abstraction process immediately means you're talking about at least two levels of abstraction. And in fact, the way in which computer scientists deal with scale and complexity and the kind of artifacts that we build and design is through layers of abstraction. And that allows us to focus at each layer only on the properties or the behaviors of interest. And then we build these complex systems by layering or other means of composition. So when we talk about abstraction, it's not just the abstraction or the particular model. It's the layers and also the relationships between the layers. And because we usually define these abstract models in very precise terms, mathematical terms, we are able to define the relationships between these layers also precisely in mathematics. In fact, all of what I said is as we do in mathematics. After all, it's not that computer scientists invented abstractions. Mathematicians and scientists use abstractions all the time. What's different is that in computing, we're always operating at least two layers of abstraction at the same time. And we're very formal about the relationship between the two layers. So this isn't anything new in some sense from what mathematicians do. But in computing, we don't just invent abstractions for the beauty and elegance of the abstraction, as mathematicians tend to strive for. We have other concerns that constrain the abstractions we choose. So in particular, I like to talk about the measures of a good abstraction in computational thinking. The first and foremost typical question a computer scientist would ask is, how efficient is this? Is this the most efficient way to solve the problem? And when I talk about efficiency, I talk about it in terms of space and time. Is this the fastest way to get from here to there? Is this a procedure which is going to require the least amount of space? So that's space and time. And I think what's most interesting right now is there's a lot of interest in what I would call the third dimension of analyzing the complexity of the kinds of abstractions we invent. And that has to do with energy. There's so much interest now, societally, from the administration, on energy. And I think computing as a discipline needs to revisit a lot of the abstractions we've invented already in terms of this third dimension. So for those of you who are researchers in computer science, I advocate that we're going to have to throw out all our algorithms textbooks and rewrite them all in terms of these three dimensions now. The other measure of goodness for the abstractions that computer scientists like to invent is correctness. After all, when you're writing a program or you're building a system, you want it to do the right thing. And so we always ask not only how fast does this, say, algorithm perform, but does it do the right thing? And what does it do the right thing mean? We usually ask, for instance, does a program compute the right answer? And that alone, answering that question alone opens up a lot of research questions. But we also want it to do something useful. So it's not enough that it does the right thing. We actually want the answer to be spit out eventually. And that's the question of, does a program eventually produce an answer? And there are complexity results that show that this isn't always an easy question to answer. And then, of course, there's the other illities, if you will, when we look at a particular abstraction and judge whether it's good or not. Simplicity and elegance, as we have for mathematics, usability, modifiability, maintainability, cost, and so on. Now, if you look at this list, you'll say, well, that's no different from good engineering. And so, in fact, computational thinking or computing in very much draws on mathematical thinking and draws on engineering thinking and comes together in terms of the automation of the kinds of abstractions we build. And what I'd like to I promise I'll just say a few more high-level remarks, and then I'll get into some concrete examples. But I like to think that computational thinking really does draw on mathematical engineering thinking. It draws on mathematics certainly as its foundations. But we, in computing, are unconstrained by the physics of the underlying we are constrained by the physics of the underlying machine. So in the end, there's going to be some machine, or there's going to be some human brain. And we are, in terms of what we can execute or automate, are going to be constrained. So a typical computer like this is going to have finite memory. It can only go so fast. And so it's constrained by the physics of this device. You know, the brain scientists are actually trying to understand the physical and intellectual limitations of our brain as an automaton. Computational thinking certainly draws on engineering since our systems interact with the real world. However, we in computing can build virtual worlds, worlds that are unconstrained by physical reality. And so when you interact in a virtual world, so how many people have heard of Second Life? Okay, Second Life is a virtual world which you can enter, and this virtual world defies the laws of physics. You have avatars who fly around. You, of course, have beings that die and come alive again. That's not like in the real world. And so what is it that in computing enables this kind of defying the laws of nature? Building worlds that are virtual. It's the software. Software enables these physical devices to be beyond the real world. When I talk about computational thinking, I really mean the concepts and not the artifacts that computer scientists produce. This is a little abstract. I promise to get a little more concrete. And finally, I talk about computational thinking as being something for everyone, everywhere. And it will be a reality when it is so integral to our endeavors that it disappears as an explicit philosophy. So being more specific, here is, unfortunately, a laundry list of what I would say computational thinking concepts. And those of you who are computer scientists or engineers or mathematicians will recognize many of these classes of abstractions. What I mean by putting this list down is not for all of you to understand all of this, but just to say that I distinguish between computational thinking and computer literacy. That is, how to use Word or Excel or PowerPoint. Computational thinking is not that. And I distinguish between computational thinking and computer programming, because computing is a lot more than computer programming. And ideally, I could come up with a better list, if you will, rather than this potpourri of concepts. I'm actually working on that as I speak. So now what I wanted to do is convince you that computational thinking has already influenced other disciplines. So let's start with one discipline influenced by many different computational methods or concepts. So who can guess what that discipline might be? Don't be shy. Scream out the answer. Scream out any answer. Yes, sir. That is an interesting answer. I'll come back to that one.
Law. Medicine. I would say science.
Medicine.
Medicine is close to my answer.
Problem-oriented medical record.
Biology.
Well, the U.S. government's been in computing, so I would
Biology. That is my answer. It's just an answer. computational thinking has greatly influenced biology to the point now we have biologists and computer scientists working together hand in hand. But more than that, we are now starting to produce a new generation of computational biologists.
Gene mapping.
Okay, and hold on, you're answering my next question, which is, my next question is, what was the tipping point? At which point did the biologists say, look over their shoulder and say, hey, you computer scientists have something to bring to the table. You computer scientists are making me think differently, making me approach my problem in a new way. Answer is?
Gene.
Right. It was the shotgun algorithm that expedited the sequencing of the human genome that all of a sudden caused a lot of interest by the biologists, by the whole medical and biology community, say, hey, there is something to computer science, to algorithms, more than just processing power. So that's the point I'm trying to make, that computing is more than just about devices and horsepower and supercomputers. And this particular algorithm was what I think the tipping point for when biology and computer science started to come together. And since then, there have been many, many examples of different kinds of computational methods, different kinds of computational models, different kinds of computational languages, different kinds of computational approaches for understanding biology. I've just listed a few. A lot of this is buzzwords, if you will. One of my I want to be a little more technical in this part of my talk, so I'm going to go through one example that's not the shotgun algorithm to show a different kind of computational model and thinking that has influenced biology. And this is very recent work. So to do that, you have to bear with me for a few slides because I'm going to now go into a slightly more technical part of my talk. And I'm going to do a little primer on this particular computational method. And it's called model checking. So I always, in my talk at this point, ask the audience, how many people have heard of model checking? OK. Oh, well, I'm surprised. OK, good. So after this slide, you will all know what model checking is, at least in the abstract. OK, so let me go through it. There's a black box. It's called the model checker. And it has two inputs. One is a finite state machine. What that means is that there are states, those are the circles, and there are transitions between the states. Those are the state transitions, the lines, the arrows. And what makes this a finite state machine is there are a finite number of circles, finite number of states. Okay, so that's one input. And it actually is critical for this technique that it be finite. The second input is a property that we would normally write in English, but because computers can't quite understand English well enough yet, we write it in a more formal language. And I picked this particular logic. It's called temporal logic. It doesn't matter. It's a formal language, a mathematical language in a logic that can reason about the ordering of events. So basically, you have these two inputs. Okay, and what happens is you describe the system of interest using this input, and you describe a desirable property using this input. So you might want to say something like, when you go to the ATM machine, eventually I get my money out. So you would say, describe the ATM machine in terms of this finite state machine and all the kinds of things you can do with it, like put your card in, punch buttons, deposit money, withdraw money. And you would describe the property, eventually get my money out, in terms of here. Okay? And ideally, for any ATM machine, you would like to know that this property holds. Okay? Ideally. Okay? That's how we like to design our systems. Of course, we know in reality there are all these bugs. Okay, so those are the two inputs. The output is either yes, every single ATM machine that has been designed will always give you your money back. But more realistically, you'll say, no, here's a bug in this ATM machine. And it says not only here's a bug, but here's an example of a sequence of steps that you would take in terms of that machine where you're not going to get your money back. Okay? And that's called a counterexample. So that's my primer on model checking. Basically, it has two inputs. You press the button, and out will say, yes, every single time you interact with this ATM machine, this property will hold. Or no, you will get into trouble if you do this sequence of events. Okay? That's a particular computational model, computational concept, computational approach, and it has been used, in fact, very successfully for hardware design. Companies like Intel and HP, Fujitsu, IBM, they all use this kind of technique for verifying and debugging hardware processor designs. So this is almost a bread and butter kind of technique in computing. And I'm going to skip that. Now, this is, for those of you who are interested in the formal definition, that's what it looks like, but okay. And there are many efficient algorithms and many efficient data structures that allow us to push a button and get that black box answer. What does that have to do with biology? Well, for the face of it, absolutely nothing. It certainly wasn't invented because there was a biological problem to solve. But it turns out that when you put computer scientists and biologists together, or when you have a person trained in both biology and computer science, sparks will fly. And that's exactly what happened with this particular person who worked in this intersection of computer science and biology, in particular model checking and protein folding. And he represents a protein that has 3 residues in this particular case in terms of this very simplistic finite state machine, where you can imagine where this state with the 3 zeros represents the folded state. And this state with the 3 ones represents the unfolded state. And the question, and these numbers in parentheses represent how much energy does it take to go from this state to this state, where you're unfolding one of the residues. Okay? And so the question is, what are all the paths, what are all the ways in which this protein can unfold itself, and what are the paths that where the protein can unfold itself using the least amount of energy? Okay, so now this is a very simple example. You could probably figure this out in your head, right? But suppose you had 76 residues. You couldn't even write that out on a piece of paper, right? There's where actually the scale of computers come in handy, because they can do that sort of calculation no problem. So in fact, they show that you can use this model checking technique to explore state spaces as large as 2 to the 76 using this kind of particular model checking algorithm, model checking approach. And this technique is a pretty recent result. You see, it's 2007. Was 14 orders of magnitude greater than comparable techniques. So this is already new stuff that we're talking about protein folding and so on. But here's where you can see sparks fly when you bring computational methods to these kinds of biological problems. Okay? So I promise it's the most technical part of my presentation. So that's one discipline, many methods. I only showed you one method. But the gentleman here already talked about algorithms, the shotgun algorithm. So let's flip it. How about one method that has influenced many disciplines? So I actually have to call on any computer scientist in the audience to help me answer this one, because I doubt the general public would know the answer. But I know there's some computer scientists in the audience, so I challenge you. What one method do you think has influenced so many disciplines today?
Conceptual modeling. Conceptual modeling.
Conceptual modeling. Of course, I have the answer I want you to say. Okay, Peter, do you have an answer?
Make it a multiple choice question.
The answer is machine learning. How many people have heard of machine learning? Oh, see, more people have heard about machine learning than model checking, so that's good, right? So machine learning has completely transformed the whole field of statistics. In fact, there's a whole department of machine learning at Carnegie Mellon, if you can believe that, within the School of Computer Science, and it's made up of faculty from computer science and statistics. And what they really do is statistical machine learning. Okay. Another example is that there are departments of statistics now at universities, for instance, Purdue, which has an excellent statistics department, who are hiring computer scientists because they see their future as in this combination of statistics and computing, in terms, particularly statistical machine learning. So we're seeing this in the next generation, if you will. So let me give you some examples of where machine learning has influenced many, many fields. So in the sciences, it's a technique that has been used to discover new brown dwarfs and fossil galaxies. This is really new scientific discoveries because of this particular technique. In medicine, it's been used for discovering and inventing these kinds of drugs and uses in these applications. In meteorology, for tornado formation. In the neurosciences, understanding the brain. So for instance, I should at least give you a one-sentence definition of machine learning, given that many people may not know it. What it is it's a technique that allows you to analyze huge data sets, large amounts of data, and find patterns and clusters in large amounts of data. And so in this particular case, what you feed this algorithm is lots and lots of fMRI scans of your brain. Okay? And what they are able to do through using machine learning is to find out what part of your brain lights up when a subject sees a noun versus a verb, or this kind of adjective versus that kind of adjective. And it's looking at lots and lots of fMRI scans that allow you to see those clusters, those patterns. It's beyond, machine learning has been used beyond science and engineering. So for instance, it's used in detecting credit card fraud. It's used on Wall Street. So there's the answer from the back of the room. It's used when you go to the supermarket and you hand the clerk your Safeway card. Do you have Safeway down here? Used to. Okay. Well, Publix. Well, right. Okay. Do they have cards? Affinity cards. They're tracking your purchases, and the coupon that you get out after your receipt it's using that kind of analysis of large amounts of data. Recommendation systems and reputation systems like Netflix, when you go to Travelocity to find out customer reviews and so on. Machine learning is even used in sports. So I don't know which basketball player this is, but maybe you do. But what they did was they videotaped lots of professional basketball players, and then the coaches would use machine learning to find out what are the skills of these professionals so they can teach those skills to their own students. And this is Lance Armstrong, who used machine learning to analyze the kind of data that he kept of himself. As you know, he's a machine, right? And he was quite mathematical and analytical in his training so that he could, really hone his skills. So that's one discipline, many methods. One method, many disciplines. Let me just give you a few more examples. Computational thinking in the sciences and beyond. In chemistry, computational methods, computational concepts have been used to actually to invent new molecular structures that would have desired chemical properties. In physics, this is one of my favorite examples. I'm going to belabor this one a little bit. In quantum computing. So there's a very young professor at MIT who works in quantum computing. He's actually in the computer science department, but he works with physicists. And in computer science, he basically there's a kind of quantum computer where you can represent the problem in terms of let's call it a graph. But you can solve it if you can solve the problem if you morph this graph into some other representation, some other graph. You can solve it more easily in this second representation. And so the idea is then how can you get this graph to be morphed into this graph? And there's a procedure that you can use that would allow you to make manipulations of each graph until finally you come in the middle and you have that intermediate. And so the physicists know about this kind of quantum computer. But the question this computer scientist asked is, how fast can you do this? This is something computer scientists ask all the time. How fast can you do it, right? I already said that that's one of the questions we always ask about efficiency in terms of space and time. The physicists never ask that question of themselves. They just know that there exists some path such that you can do that. But they didn't ask, how fast can you do it? Now, again, for the computer scientists in the audience, the reason this was such a tantalizing question to answer is if it turns out that the convergence is polynomial, it means that you might have an answer to the P equals NP question. So you can see why this young computer scientist at MIT would very much like to know the answer to that convergence question. And it turns out that it goes really, 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 really fast until this very small window where it's exponential. So, but even so, it was a very interesting question to pose. And now he tells me that the physicists are going around asking, how fast is all their little convergence questions? So this to me is a deep way of computational thinking influencing other people's thinking. Because you ask these basic questions that we would ask, and had the answer been in polynomial, then wow, what a breakthrough in computer science. Okay, so we see it in mathematics, we see it in engineering, and I think we're going to see more of it in all other fields. In society, like economics, Right now, in fact, tomorrow and Friday, there's a workshop at Cornell on computer science and economics that NSF is helping to sponsor. And we're seeing a lot of the theories of economics and models of economics, in fact, well, we already know that some of them are not applying to our real world, but they're certainly not necessarily applicable to, say, the internet and internet economics. And so there's all of a sudden this new interest, or a completely new interest, in revisiting economic models and theories in terms of computing models and vice versa. So for instance, we are very much using game theoretic models in looking at lots of problems in computer science, game theory from economics. But many of the direct relationships between economics and computer science has to do with things like ad placement and keyword auctions and so on. So for instance, when you type into Google and you do a search, maybe you realize that to the right of the results of your search, you have all these ads. Well, companies actually bid on where they want their company to be listed in that list of ads. You pay a lot to be listed number 1. But maybe it doesn't matter if you're listed number 1 or 2. You pay a little less, you're listed number 2, you're still number 2, you're up there, right? And so that's the kind of game theoretic thinking that people are doing in computer science. In law, we're seeing computational thinking. And in the humanities, again, in the sense of digging into the data challenge, is analyzing lots and lots of data. So what I wanted to make mention of, so that to me, I just, through lots of examples, I'm trying to convince you that computational thinking has already influenced a lot of disciplines, and there's a lot more to come. But what about this vision of mine with respect to education? And this is where it gets pretty grandiose. So first of all, I actually think that it's not just for, if you will, undergraduates. It's certainly not just for undergraduates in computer science. And I think the real challenge is K through 12. If I really wanted to push my vision to the limit. And so I now pose this question and challenge for the computing community, which is, what is an effective way of learning computational thinking by K through 12 students, or teaching it to K through 12 students by teachers? And I divide this question into 2 parts. First of all, what are the concepts that would make sense to teach to K through 12 students? And more importantly, what is the progression of concepts that we can teach so that we can build from year to year, from grade to grade, on the concepts they've learned already? My analogy is mathematics. We know in kindergarten we can teach numbers. By 7th grade we can teach algebra. By 12th grade we can teach calculus in mathematics. We've somehow figured this out, the math profession, but more than the math profession, the people who understand childhood development and how children's brains learn over time. What abstractions can they learn when they're 5 years old versus what abstractions can they learn when they're 18 years old? And we've somehow figured this all out. But we don't have that kind of analogy in computer science. And so this is my challenge to the community. First, we have to figure out what those concepts are, and then we have to stack them or sequence them in a way that reflects the maturity of how our brains develop. So that's part 1. Part 2 is, of course, in computing, we have the computer, the tool. And we'd like to enhance the learning of computational thinking using the tool. But we also don't want to fool ourselves into thinking just because we know how to use a tool, we understand computing, or we have an understanding of computational concepts. So we need to be careful. The analogy there is, just because we know how to use a calculator doesn't actually actually mean we know how to add and multiply and so on. And that's, in fact, a scary thing when I go to the stores these days and right. So you know the scary stories. I have lots of them for you. It alarms me what our kids don't know in terms of mathematics. Okay. So I actually have been engaging the computer science community along with the national academies to do some workshops and working with educators and cognitive scientists on this question. Because computer scientists have no clue about how children learn. They have no clue about how to teach K through 12 students. So they are the last people to ask, to help. But they're the ones who have to understand what the concepts are. So my suggestion more broadly for the nation with respect to STEM education is really, right now, STEM stands for science, technology, engineering, and mathematics. Add computer science to STEM. This is yet another ambitious goal of mine. And as you know, to change anything in the United States public school systems means changing 10,000 school districts, or however many there are, one by one. Okay. Well, there are other ways of doing it. I think the time is right. I think society needs more STEM-capable students and teachers. The administration, the new administration, really understands the importance of STEM. And this professional organization of computer science, ACM, is actually leading the promotion of this vision. They held an event on the Hill recently, and they've been very engaged with congressional legislation and so on. So we can only cross our fingers and hope. This event on the Hill was actually sponsored by various organizations, all computer professional organizations, Microsoft, and so on. Okay, so let me just give you an example of computational thinking in daily life. Here is me at NSF getting my coffee in the morning. Okay, so this is a true story. So first I get my cup, and then I put milk in it. Now, I didn't used to do this, but the NSF stations were set up that I would put my milk in first instead of last. And then I get the coffee, and then I get the sugar and cream. Then I get my lid, and then my napkin, and then I leave. Okay, so here's my path. Now, what's wrong with this picture? It's not efficient. Bravo. Okay, so the first thing, I look at this as a computer science, and I think one word, actually. So is anyone in the computer science community in the audience want to say, what would you say when you look at that? It's inefficient. And in computer science, the way we would, by the way, it's even worse with two people, right? And this is a real frustration because, I'm standing there and you want your caffeine in the morning and there's someone in the way, like getting coffee or soda. It's like, get out of my way. But you have to be patient. Anyway, so what do I think? I think pipelining, that this is a standard computational concept. And basically, it allows you to stage things so that you don't have to go back and forth. Okay? Now, not only do I look at this and think pipelining, but I look at this and I say, well, actually, the coffee station is fixed. It's bolted into the counter. So is the soda machine. But all these other stations, if you will, are movable. So I think, what's the minimum number of stations I need to move such that I can create a pipeline? This is like, overdoing it. Oh, and then I think, the answer is 1. Then I think, but is that actually the most efficient pipeline? Because it doesn't take a lot to get a cup. But it takes a lot of time. But it takes more time to pour the coffee. And so I think I'm going overboard here. So yes, the answer is you only have to move the lids, and then you have this nice pipeline. It is not the most, it's not the most efficient in terms of time, but it works. And by the way, yes, I did tell the NSF cafeteria people, I said, you only have to move the lids. And they ignored me completely. And in fact, they did rearrange the stations, and they made it worse. So much for computational thinking in the NSF cafeteria. So this is videotaped. Okay. However, I do want to say that we do think computationally at NSF, and I just want to brag a little bit about this one program that we put out in fiscal year 08, and it's called Cyber-Enabled Discovery and Innovation, CDI, and in a nutshell, it is computational thinking for science and engineering. What it really recognizes is a whole paradigm shift in the way science and engineering is conducted and certainly will be conducted in the future. And that is, it's not just our metal tools, transistors, networks, supercomputers, and so on. It's our mental tools, the concepts, be they algorithms or models or abstractions and methods. And this particular program requires above and beyond the normal kind of proposal, innovation in computational thinking, and to advance more than one science or engineering discipline. The first year, we were able to invest almost $50 million. It's a foundation-wide program. Every single director and office participated. And here's a list of disciplines that were represented by the awards we made in the first year. And this is incredibly gratifying to see, because they were all these projects were using computational thinking to advance not just computing, but all these other fields. And some of these actually did address societal challenges like cancer, climate change, energy, environment, persons with disabilities, and water. So, and in terms of education, we also have been working with the community on promoting computational thinking, especially at K through 12. I'm not going to elaborate on this. I've talked about our efforts at the K through 12 level, in particular with the national academies, but there are other organizations that are all collectively trying to get behind maybe not so much specifically computational thinking, but the point that computer science is a lot more than computer programming, and that what we are teaching right now to the high school students is really does not do justice to the field of computer science. So the high school students and high school teachers are not really getting a good glimpse of what the field is all about. My little 3-page article has been translated in Chinese and French. And I was really glad to see that the recent research assessment on computer science in the UK actually said quite explicitly that computational thinking is influencing all disciplines. So now this is just a mere, flag waving, spread the word, appeal to the audience and all your friends and colleagues to help spread the word. And I'm happy to answer questions on it. But I'm not done yet. Because remember, the title of my talk was Computational Thinking and Thinking About Computing. So I'm going to talk about, this is the penultimate word now, thinking about computing. And I'm just going to preface this quite briefly. In computer science, it's very easy. In computing, it's very easy to get swept away by all the technological advances that we make. Faster and faster processors, faster and faster networks, bigger and bigger memory, and cool devices that we can wear and put in our pockets and embed in us. So that's what I call the technology drivers of our field. And as long as technology advances, we in computing will continue to have research challenges ahead of us. No problem. At the same time, societal expectations of computing and computer scientists have grown also. So now there's an expectation of 24/7 reliability, connectivity, 100% of the time, 100% availability. Nothing else should ever go down. I want instantaneous response. I want to be able to store everything. Whoa! We can't do all that yet, although society expects of that of us. So we have these societal drivers to our field as well. So I talk about technology drivers, societal drivers, but often what people miss is that we also have what I would call science drivers to our field. Fundamental questions that underlie the kinds of problems and challenges that face us. So I started this very short list of what I call 5 deep questions in computing, just to start a conversation on what are the science drivers in computer science. And the first one is probably the most fundamental, which is the question of what is computable. And to answer this, you actually have to answer it with respect to the automaton underneath the machine, if you will, the automata underneath by which you are determining computability. And the reason this is such an interesting question now is that people are now thinking that when I talk about a computer and ask what is computable with respect to this computer, that this computer could actually have humans as part of the intelligence. So now ask the question, when you think about my network of humans and computers working together, now ask the question, what is computable? We can answer for a specific class of machines. We can very precisely answer that question. But for machines that are kind of beyond what we typically study in computer science and theory, it's really an interesting question. And if there's no institute better than IHMC to tackle this, it's really, this is your question. OK, within this question is the question of the P equals NP problem. This is a very technical question, a technical problem that has been long-standing in our field since the inception of our field. We have no answer to this question. Moreover, we know that there's certain mathematical techniques or proof techniques that will not answer that question. So the implications of whether the answer is yes, P equals NP, or no, P does not equal NP, have very serious implications, practical implications in one direction and theoretical implications in the other. What is intelligence? This is a question that has also been long-standing in our field. It really spawned the whole area of artificial intelligence or machine intelligence. And now we are revisiting this question because of these new kinds of machines that we're talking about. What is information? This again, we thought that we had this nailed down with Shannon's information theory. But Shannon's information theory was defined and designed and developed to answer a specific question about communicating bits over a noisy channel. And we sort of fallen into this complacency thinking, oh, we've got Shannon's information theory to answer this question. But we don't when we have people, for instance, my fellow assistant director in biology, Jim Collins, who gave a talk here before, who goes around and talks about biology as an information science. And that's very intriguing to me, Because computer scientists think about information in terms of just zeros and ones. In the end, it's just zeros and ones. But in biology, you don't think that. You think that there are these natural organisms that take in an input, massage it, eat, and then produce some effect on the environment. And somehow there's information processing there. Okay, but what is that information then? And it's not merely digitizing nature, if you will. That's the superficial answer. So I think this is all very interesting. And finally, there's this question of complexity. How can we build complex systems simply? We right now know how to build complex systems that are quite complicated. And it's been a huge challenge, especially to the software engineering part of computer science, to try to really tackle that question. So those are my 5 deep questions. I'm happy to elaborate on any of them. Let me just close now. Here are my 3 drivers of computing. And let me just close now with saying that the future for computing is quite bright. I like to talk about the 7 A's. Anytime, anywhere, affordable, access to anything by anyone authorized. This is a bit mouthy, but the real difference between this and what people might call pervasive computing or ubiquitous computing as we know it from the late 90s even, is the words affordable and authorized. Because now we are truly talking about computing for the young and the old, for the able and disabled, for the literate and illiterate. And really, the best is yet to come. So thank you very much.
We have time for a couple questions. Questions? Tracy, there's one back here, too.
The man in the red shirt had his finger up first.
Real simply, that last point on the 5 points.
Yes.
Stephen Wolfram created that new kind of science kind of thing with his rules and his cellular automata. How does that play into what you're talking about?
That is a kind of computational model that allows you to model a certain communication pattern between cells so that you can solve certain kinds of problems. That's a very vague way of saying it, but it is a computational model, a particular technique. It's particularly good for what I would call emergent behavior of complex systems. And so it very much fits in with the last question. And it's really a research area right now to understand what I would call more generally emergent behavior of complex systems.
Professor, thank you ever so much for coming down to visit with us.
You're welcome.
And your talk's been wonderful, truly wonderful. The $527 million in funding that you, I don't know, is that what you've asked for? But here's the full question. What have you asked for? And how much could you comfortably spend if you got what you asked for? And how much, if any, have you given down to us here in Pensacola?
Are those all serious questions? Okay, so obviously I cannot answer the first question in terms of how much I have asked for. All the information that's public is public, so you can know what our presidential request is for FY10. And there's a whole way in which the budget is decided for the National Science Foundation. There's a budget cycle that we follow, and it will probably not be for a while that we will actually know how much we get. Let's see, that was the first question. How much did we ask for? How much could we spend were we to get whatever we get? I can tell you, I can spend it all. And not only that, but more importantly, I can spend it wisely. That's what you really want to know, I think. And the third question is, how much has Pensacola benefited from, say, the National Science Foundation? I actually do not know the answer to that question. Sorry. Next question, easier, please. So Peter, you're going to get plenty of chances. Maybe, yeah.
Alec Yasinsak from University of South Alabama. I liked your talk about machine learning, and you can expect a proposal from us on machine learning in the near future, because that's something you're very interested in. And you talked about disciplines that are multidisciplinary areas that would fit with computational thinking. Give us your intuition on what you think the target-rich environment that hasn't been yet emerged as a area for computational thinking, research, and innovation.
An area that hasn't been affected. Well, that's what I can say is this, that every time I think of a discipline, I can certainly see how computational thinking might influence it. I think it's just emerging now in the humanities, the arts, literature, history, and so on. And the way it's happening right now is, if you will, the obvious, machine learning applied to lots of data. But I think that is a good foot in the door. Because what I hope is, once people realize that, oh my God, we can discover new historical patterns, or we can create new kinds of art that with the techniques that they are taught or learn in computing, that they ask us in computer science, what more do you have? What more can we do with your techniques so that we can make more discoveries? So I would say it's coming. And again, let me put my other hat on, which is the Carnegie Mellon hat. It's certainly, computing has certainly pervaded Carnegie Mellon. We're kind of the big gorilla on campus, if you will. And I can list for you easily 20 different either degrees or majors or minors or courses that have the word computational X in it. So there's computational photography, computational astrophysics. I mean, I actually have the list on my laptop. It's pretty amazing. Of course, Carnegie Mellon is a little odd, but I just see that it's only limited by your imagination. That's how big I think it is.
Last question.
Yeah, just one quick question. With computational thinking, do you see that affecting some of the basic approaches to research methodology in any way?
Yes, absolutely. So we talk about, at the National Science Foundation, we talk about the third pillar in science: theory, experimentation, and computation. That is how fundamental we see science and engineering in the future. And so if that's true, then scientists and engineers today, the graduate students, the students, undergraduates, need to be trained in terms of not, how to prove a theorem or how to run an experiment in the lab, but also the computational methods that will allow you to model, simulate, predict, and so on using computation. So I think it's quite fundamental transformative, if you will.
Let's thank our speaker.
Thank you. Bring together the intelligence of a human with the intelligence of a machine, networks of them, that itself is collective intelligence. That could be an automaton in my world of automation. So that's quite a powerful notion, very unusual, and I'm going to save that thought because I'm going to come back to it at the end of my talk. As I said, that's just part of the picture with respect to computing or computer science. But that's really not what I'm going to talk about for the most of my talk. I'm really going to focus on the abstraction part of computing. Computational thinking is really all about the process of abstraction. And let me just explain what I mean by that. First of all, it is choosing the right abstraction. Not every abstraction is going to be appropriate for the problem that you're trying to solve. So first you choose an abstraction. And then, by definition, an abstraction is ignoring irrelevant detail and encapsulating in this abstract model the details of importance. That means I'm in the abstraction that then tells us more about the physical world phenomenon that we're actually modeling. When I talk about automation, and this is a whole other talk I could give, so I'm just going to give this as a side note. When I talk about automation, I'm very careful to include that the automaton can be a human, or it could be a machine. After all, humans compute. We may not be as fast as machines, but in fact, there are some ways that humans are much, much better computers than machines. In other words, there are still some tasks that humans can solve better than machines. Vision is one example. Speech, natural language processing. A lot of the challenges of artificial intelligence are put forth for us as scientists because machines still can't do them as well as humans. But that's, if you will, just the base case. I also like to talk about humans and machines together. In fact, networks of humans and machines together as an automaton. So think now that you can immediately talking about at least two levels of interest. The level I'm ignoring the detail from and the level of interest. So the abstraction process immediately means you're talking about at least two levels of abstraction. And in fact, the way in which computer scientists deal with scale and complexity and the kind of artifacts that we build and design is through layers of abstraction. And that allows us to focus at each layer only on the properties or the behaviors of interest. And then we build these complex systems by layering or other means of composition. So when we talk about abstraction, it's not just the abstraction or the particular model. It's the layers and also the relationships between the layers. And because we usually define these abstract models in very precise terms, mathematical terms, we are able to define the relationships between these layers also precisely in mathematics. In fact, all of what I said is able to spread of computational thinking. Now, this vision has grave implications with respect to the research in any discipline that we conduct, as well as educational implications, which I will talk about a little bit, especially with respect to K through 12. And so if you are interested in this talk that I'm giving today, I wrote a very short article. It's only 3 pages long that appeared in CACM a few years ago. And it really captures a lot of what I'm going to say today. So computing. Let's first talk about computing. Computing is what I like to call the automation of abstractions. This is quite abstract, and I will try to explain what I mean by this. But I like to think about computing in terms of these two A's, automation and abstractions. And it really is this feedback loop that one has when you're abstracting from some physical world phenomenon, creating a mathematical model of this physical world phenomenon, and then analyzing the abstraction, doing sorts of manipulations of this abstraction, and in fact, automating. Inviting me to be here, and it's a real delight. It's my first time in Pensacola, so it's a real pleasure to be here, and I've enjoyed my stay so far. So I'm going to talk about computational thinking and a little bit about thinking about computing. And I'm going to start right away. So I'm going to start with my grand vision, that computational thinking will be a fundamental skill used by everyone in the world by the middle of the 21st century. Just like reading, writing, and arithmetic. That's how fundamental I imagine computational thinking will be, or should be. And of course, it's an incestuous vision in that computing and computers will enable